Okay, so this is a linearization question to follow on with the previous homework assignment where we're going to come up with a third method to determine the spring constant of this spring. So we have this lab group that's going to compress the spring vertically on a table and release it, which causes it to jump. When the spring is compressed a distance x from its uncompressed length, which we're going to call LO, and is released, the top of the spring rises to a maximum height h above the point of its maximum compression. And the students compress and release the spring multiple times, each time attaching a different mass m to the top of the spring and measuring the height to which it rises. So this is a conservation of energy because we're turning elastic energy as soon as it's being released into kinetic energy, which is gradually transforming into the gravitational energy as it reaches its highest point. So if we set up a conservation of energy equation for part A, we're going to have Ki plus Ui equals K final plus U final. Initially, the spring is just compressed on the table, so it has elastic energy, but it's not moving, so there's no kinetic energy. And at the highest point, it has gravitational energy, but at the highest point, it's also not moving, so it has no final kinetic energy. It only has kinetic energy in between those points. So we're turning Ui, the elastic energy, into Uf, the gravitational energy. So when we plug in the formulas, we have 1/2 kx squared is equal to mgh, and it's asking you to solve for the height h in terms of everything else. So let's just divide both sides of this by mg so that the mg's will cancel out, and we're left with h is equal to, I'll bring this 2 down into the denominator, so we have h equals kx squared over 2 mg for part A. So that's the equation that we're going to end up using to linearize this graph. Remember, sometimes you have to derive the equation in order to linearize it. Other times, like with the period of a mass spring system, you already know the equation. It's given on the formula sheet, and you just linearize that equation. Part B, describe a procedure for accurately measuring the height h in this experiment. Given that the spring is only momentarily at that maximum height, well, obviously you need something like a meter stick placed behind it so you can see what it gets up to. But if you just say a meter stick, that's not enough because, and it specifically tells you in the question, it's only momentarily at that height. So you want to also make sure you indicate something like a recording device, like a video camera, to so that you can play it back in slow motion or frame by frame and figure out exactly what that maximum height is. Alternatively, you could use something like a motion detector positioned above it, because that should tell you specifically what the height is at every passing instant of time, so you should be able to get the height pretty easily that way. Part C, with the spring compressed a distance of 4 centimeters in each trial, the students obtained the following data for different values of m attached to the top of the spring. I worded this incorrectly when I was making this. We actually have to do part D first, and then go back and fill in the table for part C. So, part D, indicate which quantities should be graphed to determine an experimental value for the spring constant. We are measuring the height as a function of mass. Notice that height is on the left side of the equation, mass is in the denominator on the right side of the equation. Everything else in that equation is constant. We have the spring constant, which we're trying to solve for. X is the compression of the spring, which was told for every single trial is going to be 4 centimeters, or 0.04 meters. And then we have G, which is, since this is a lab-based question, we should be using 9.8 for the G. But again, it's okay if you want to use 10. You're just getting an answer that's a little bit further off from the correct value. So if we take this equation and just match it with y equals mx plus b, and actually I'm going to use s for slope, x plus b, and I'm not going to put the plus b on there since we have no plus b we have no pluses in the original equation. On the y-axis, on the vertical axis, I'm going to put the height, so we can record that under part D. We want to have the height. That should be measured in meters, not in centimeters, as it's expressed in the table. And on the horizontal axis, because Mass is the other thing that is being changed. Mass is in the denominator, so we actually need to graph 1 over m, which is going to have units of 1 over kilograms or inverse kilograms. And then that means the slope of this graph is going to be everything else, which will be kx squared over 2g for the slope. So even though it doesn't specifically ask you yet for the slope, when we are solving for this in one of the last parts of the problem, we want to set the slope equal to kx squared over 2g. So now let's go back to part C and fill in the table. Notice that all of the masses are given in grams, so we first have to convert them into kilograms, and then we have to take 1 over that in kilograms. So let's just do the first two, for example. So 5 grams is going to have a mass of 0.005 kilograms. So in that first row of the table, where you write 1 over m in units of inverse kilograms, 1 over 0.005 is 200. So the square just above the 5 should have a 200 in it. Let's just do one more of these. Next one in the table is 10 grams, which is 0.01 kilograms. When you do 1 over m in units of kilogram, inverse kilograms, 1 over 0.01 is 100. So that you should have a 100 over the 10. The remaining numbers are, I'll give you them just without working out, 50, 33.3, 25, and 20 for everything else in that top row of the table. In the bottom row of the table, the height doesn't really change that much because we said on the vertical axis we're going to have height, but we did say it needs to be measured in meters, so you just need to convert all those heights from centimeters into meters, so like 0.65, 0.33, and so on up to 0.06. In part E, this is where we're going to want to go ahead and plot those points. You should get something that has a few closer together, and then they get a little spread apart as you go along, but it should form a pretty straight line. Let me draw that best fit line a little bit better. Should form a pretty straight line. And when you find the slope of this line, remember you want to take 2 points on the line that are not data points as far apart as possible. So if your line passes through the origin, that's a good point to take. And then take another point somewhere up here and do rise over run. And when I did this, I got a slope of approximately 0.0033. Remember, on the graph, you should have your axes labeled. So you want to put height in meters on the vertical axis. You want to put 1 over the mass in units of inverse kilograms on the horizontal axis. And finally, we're going to go back to this slope equation, and we're going to rearrange that equation to get k by itself, since k is what we're looking for. The slope, I'm just going to call that s. So when we get k by itself, we want to multiply both sides by 2g. So we have 2gs divided by, looks like it's just going to be divided by x squared. So you're going to plug in 2 times 9.8 times 0.0033 divided by x. That was the compression. Remember, it was 4 centimeters. That needs to be converted into meters. 0.04 squared, and that gives me an approximate k value of about 40.4. Don't forget the units on this. When I was checking homework for this last assignment, I noticed that most people did not have units on the final answer, and they will sometimes take off points for that. It is 40.4 newtons per meter. Make sure you understand this linearization process well. You're going to see it again and again and again on this test and on future tests, and a lot of people still seem to be having a lot of difficulty with it.